Today we'll discuss section 4.7. In section 4.7, we describe all phase portraits of the following system of equations. X dot is equal to AX, where A is a square matrix. Now, question is, what is a phase portrait? A phase portrait, in simple words, is a collection of all orbits. Now, next question is, what is an orbit? Let us go back to the previous section. In the previous section, we started with this system of differential equations. And then we consider the following triples: t, x of t, y of t, where x of t and y of t are solutions of this system. Note that these triples trace a curve in the three-dimensional vector space. Let us consider the projection of this three-dimensional curve to the xy plane that we call phase plane. We call this projection the orbit or trajectory. So for a particular solution, we get a three-dimensional curve and its projection is the orbit. The collection of all possible orbits is a phase portrait. So once again, in this section, we deal only with 2x2 systems of linear differential equations. In order to describe a phase portrait, step 1, find eigenvalues of A. We consider the following cases. Case 1. Suppose both eigenvalues are real, distinct, and negative. In this case, we draw two lines. Line number 1 is parallel to any vector from the eigenspace corresponding to lambda 1. Line number 2 is parallel to a vector from the eigenspace corresponding to lambda 2. L1, L1 prime, L2 prime, and L2 are 4 orbits. All other orbits go closer and closer to the origin, approaching L1 or L1 prime. Repeat once again. Step 1, find eigenvalues. If both eigenvalues are negative, distinct, and real, we find the corresponding eigenspaces, pick an eigenvector from the eigenspace corresponding to lambda 1, draw this line which goes through the origin and parallel to this vector, draw this line which goes through the origin and parallel to an eigenvector from the eigenspace corresponding to lambda 2, and then draw these curves. We have the following orbits: orbit number 1, orbit number 2, orbit number 3, orbit number 4, and then these curves represent other orbits. Of course, here on this picture, we have few out of infinitely many orbits, but essentially shapes of orbits resemble the curves from this picture. Another important thing, since both eigenvalues are negative, all arrows point towards the origin. Subcase number 2, if both eigenvalues are real, distinct, and positive, we'll have same picture, but the arrows will point in the opposite direction, away from the origin. Any questions here?
Professor, what exactly is the relation between our eigenvectors and this phase plane stuff? Like how do those intersect exactly? I mean, just how come our eigenvectors and our eigenspaces are related to these phase plane?
Probably in order to answer your question, let us take a look at this example. This example gives you at least some insight. So here we have a 2x2 system. We apply the standard procedure in order to find all eigenvalues. Then for each eigenvalue, we find the corresponding eigenspace. One can check, work is in the appendix, that V1 is an eigenvector for -3 and V2 is an eigenvector for -6. In order to sketch the phase portrait, draw this line, which is parallel to V1, draw this line, which is parallel to V2, and then sketch the curves. Now, in this problem, we don't really need this, but in order to answer your question, please take a look at the formulas for the general solutions. So in our case, x1 is this, x2 is this. If you plug in many values for t here and find the corresponding values of x1 and x2, and then plot these points on the x1, x2 plane, you will get these lines and these curves. Note that over here, we can plug in whatever instead of C1 and whatever instead of C2. Observe that if C2 is 0, these two terms disappear. If C1 is 1, then x1 is this, x2 is same thing. So, since x1 and x2 is same expression, x1 is equal to x2. And the graph of x1 is equal to x2 is this line. Similarly, if C1 is equal to 0, and C2 is equal to 1, then x1 is this, x2 is 4 times this. Therefore, x2 is 4 times x1. The graph of this equation is this.
Okay, yeah, that helps.
If C1 and C2 are different from 0, 1 or 1, 0, we'll come up with these curves if we plug in many values for t. Does this answer your question?
Yes.
Other questions?
Can you explain the direction of the arrows again?
Yes. If both lambdas are negative, all arrows point towards the origin. If both lambdas are positive, in the opposite direction.
Okay, right. Thank you.
And once again, observe that this picture perfectly corresponds to theorem 1 from section 4.2. If both eigenvalues are negative, all solutions are stable. Indeed, all curves converge to the origin. Number 2, if at least one eigenvalue is positive, in our case, both eigenvalues are positive, all arrows will point away from the origin, which means all solutions are unstable. Does this make sense?
Yes.
Other questions?
So L1 and L2 are orbits?
Yes. L1, L2, L2 prime, L1 prime are orbits.
Okay.
Other questions?
What does an orbit mean again?
Yes, an orbit is the following. Please take a look at this. Once again. We go to section 4.4. Step 1, we start with this system. We find solutions of the system. We find a particular solution of the system, x of t, y of t. These are some functions on t. And then consider the following triples: t, x of t, y of t. Plug in all values for t from the domain of x and y. These points will trace a curve in the three-dimensional space. We project this curve on the xy plane. This projection is the orbit. Now, phase plane is the collection of all orbits. So these curves are projections of three-dimensional curves on the x1, x2 plane. Does this answer your question?
Yeah, thank you.
Other questions?
Yeah, so you said that the phase portrait is a collection of all orbits.
Yes.
So how do you get more than one orbit if in this case we only have one?
Please take a look at this. So if we fix some value of C1 and some value of C2, we'll get only one orbit.
Oh, okay.
If C1 is 1, C2 is 0, we get this. Vice versa. If C1 is 0, C2 is 1, we'll get this. For other combinations of C1 and C2, we'll get these curves.
Okay, thanks.
So once again, on this picture, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 orbits out of infinitely many. This picture gives you an idea how orbits look. Other questions?
So a phase portrait is what you use to describe the behavior of all orbits, right?
Yes, it gives us an idea how do orbits look. Was that your question?
Yeah.
Next, case 2. Both eigenvalues are real, negative, and equal. In this case, we consider two subcases. We find the eigenspace. If this eigenspace is two-dimensional, here is the phase portrait. If this eigenspace is one-dimensional, here is the phase portrait. This line is parallel to any vector from our eigenspace. So compare picture A and picture B. Over here on picture B, we have just one line, which is parallel to any vector from the eigenspace. Because our eigenspace is one-dimensional, therefore all vectors are parallel to each other because they are multiples of a basis vector. Compare with A. Over here, we have infinitely many lines. Each orbit is a ray. Orbit number 1, orbit number 2, orbit number 3, and so on. Again, we have few out of infinitely many orbits. On B, there are two orbits, orbit number 1 and orbit number 2, that are lines, or better to say rays. All other orbits are curves. Next. If both lambdas are equal and greater than 0, we have same pictures, but the arrays point away from the origin. So in this case, all solutions are stable. In this case, all solutions are not stable. Case 3. Both eigenvalues are real, but one is lesser than 0, the other is greater than 0. In this case, we have this picture where L1 and L1 prime are parallel to any eigenvector corresponding to lambda 1. L2 prime are parallel to any eigenvector corresponding to a lambda 2. The arrows on L1 and L1 prime point towards the origin. On L2 and L2 prime away from the origin. Looking at these curves, these arrows go from L1 to L2. From L1 to L2, from L1 to L2, from L1 to L2, and from L1 to L2. For example, here's a system. We apply the standard procedure to find eigenvalues. The eigenvalues are -2 and 4. Corresponding eigenvectors are V1 and V2. We plot the lines first. L1 is parallel to V1, L2 is parallel to V2, and then we sketch the curves. By the way, in this case, all solutions are not stable because one eigenvalue is negative, but the other eigenvalue is positive, according to B from theorem 1. We can come up with the same conclusion looking at the picture. Let me remind you that a solution is stable if every other solution remains close. Here, it's impossible to find an orbit which is close to any other orbit, no matter what is t. Any questions here?
Okay, is this on a two-dimensional plane?
Yes, once again, an orbit is a projection of the three-dimensional curve on the phase plane.
Ah, okay, yeah, I see it.
Other questions?
It looks to me like some of the orbits are getting close to L2 and L2 prime.
Yes.
Is that
it's
wrong?
exactly what we see here. So these curves start close to L1 and then go closer and closer to L2 prime.
Oh, but they're not like starting at L2.
Basically, here we don't really care about what happens if, say, t is equal to 0. Most important thing for us, what happens if t is big?
I'm confused because I thought stable meant that the orbits get farther away from each other, right, as t is big.
Let us go back to the definition. Please take a look at this word, every. The solution is stable if every other solution remains close. It's not the case. For example, pick this curve. Yes, this curve goes closer and closer to this one. But it is still far from, say, this. Does this make sense?
Yes, that makes sense. Okay, thank you.
Next example. Case 4. Eigenvalues are complex. We split this case into 3 subcases. Subcase number 1, alpha is 0. Subcase number 2, alpha is negative. Subcase number 3, alpha is positive, where alpha is this. By the way, observe that since we are talking about 2 by 2 systems, if one of the roots is not a real number, the other root is necessarily not a real number. Moreover, if one of the roots is of the form alpha plus I beta, the other is its conjugate, means alpha minus I beta. So there are 3 cases. Alpha is 0, alpha is negative, alpha is positive. Please take a look at these 6 pictures. Column A is about case number 1, alpha is 0. Column number 2, alpha is negative. Column number 3, alpha is positive. What's the difference between rows? Let us go back to this. Remember, A is the following matrix, A, B, C, D. Now, we look at this number, C. If C is positive, it's row number 1. If C is negative, it's row number 2. In row number 1, all pointers go in the counterclockwise direction. In row number 2, clockwise direction. Let us consider the following example. Here is a system. We apply the standard procedure in order to find all eigenvalues. Note that alpha here is negative. Conclusion, this is column number 2. Also observe that C is also negative, means a row number 2. So we have this picture and it's exactly what we see here. Last observation, note that in columns number 1 and number 2, all solutions are stable. In column number 3, all solutions are not stable. Why solutions are stable here in column number 1? Because they stay close to each other. Analytically, we have case number 1 if alpha is equal to 0. Note that if alpha is equal to 0, this is case C in the theorem. Observe also that in this case, we will get 2 distinct complex numbers. Each complex number will have multiplicity 1, and the corresponding eigenspaces cannot have dimension lesser than 1. So, in case A, dimension of each eigenspace is equal to the corresponding multiplicity, therefore all solutions are stable. So, in case for A, all solutions are stable, we can come up with this conclusion looking at this picture and looking at theorem 1C. Over here, in column number 2, all solutions are stable because alpha or real part is negative. In C, all solutions are not stable because real part is positive. Any questions here?
What happens if they're both negative, both 0, both alpha and beta, and both roots?
Excellent question. So your question is, what if alpha is equal to 0 and beta is equal to 0? Is this your question?
Yes.
Guys, excellent question. For some reason, we do not discuss in this section the case when numbers are equal to 0. You can take a look at other sources.
Okay, thank you.